Okay, good morning to all of you. Are you able to see me? Are you able to hear me? Okay, so this could be our last lecture because chapter 6 is a very short one. Okay, so chapter 6 is about the base drive circuit. So basically, the base drive circuit function is to ensure that you have like a driver. Okay, like a if you're talking about the motor, right? Motor, we have the motor driver to control the speed, to control the torque. So the same thing applies, the same concept applied here. When you have a MOSFET, you have a BJT, you also need to have a proper driver, okay, to ensure that the BJT or MOSFET can work as a switch. When I want you to turn on, you can turn on as soon as possible. When to be turned off, it should be able to turn off as fast as possible as well, without the energy being stored inside the PN junction.
Because I go to activity, I think come out everything. So I click this one.
Okay. All right. Before I continue, just to remind you, so this week is already like a week 11, the new week 11. So your everything, all the deadline is due by next week. So for example, your group assignment submission deadline will be on 17th of April, which is on next week. So because this chapter is very short, so I will have a planning for to end our topic. Okay, right. So my planning is like this. Okay. So today we will complete the chapter 6 about the base drive circuit. However, just for your information, this chapter actually is initially planned for the final exam, the face-to-face final exam. Okay. However, because now we no longer had the final exam, so this chapter actually will not come out in your final assessment. Okay, just for your noting for this. Okay, the base drive circuit, but this is only involved a very small portion of the entire power electronics syllabi. Okay, and then so today I will just to quickly discuss about the concept behind the base drive circuit to finish it. So that means we will end our lecture, okay, for power electronic. So that by Thursday there will be no class, okay, and then on next Tuesday also no class. Is for your own revision. Of course, if you have any question, you can always raise the issue and then let me know. So I'll try to answer your question. So that I will need to have one last revision on 16th of April. Okay, the last on week 12. Okay, one day before your assignment submission deadline. Okay, the reason I'll call for this final revision is because that there are certain things which is still unclear yet, such as the format for the final assessment. Okay, the FA, okay, final assessment format, and also what kind of the final assessment to be conducted, such as we have the quiz, we have the multiple choice answer, we have like extended assignment kind of thing. So by the way, the faculty are still try to standardize and also to finalize the final assessment. So that's why. So I cannot tell you exactly the format by Thursday, by this Thursday. That's why there will be no class on this Thursday and no class on the next. Okay, sorry, I have to record it down first. Okay, so that some of you may be able to. Okay, I think you already recorded. Okay. So again, I repeat. So because of a lot of the format haven't been finalized, so the faculty need to call for a few meetings to standardize the format. So that's why I will call the final revision on next week. Okay, next Thursday. Okay, remember this jot down this deadline. Yeah, next Thursday. This will be the final discussion and final revision for your entire chapters. Then from there, I will tell you what kind of assessment we have. Okay, so as so far, I already prepared the MCA. Okay, multiple choice answer. So we have 20 questions for you to answer within how many minutes. Then you have to submit through the Google form kind of things. You have this kind of the planning at the moment, but haven't confirmed yet because I still need to get the approval from the faculty, from the university. That's why we need to wait until the next Thursday so that everything can be clear. Okay, so far we have the MCA, we have the extended assignment, something like a group assignment also, but it's another assignment. Okay, but this having the shorter duration, maybe 1 week only. So this extended assignment maybe something like I want you to design the like a motor driver, okay, and then to connect on the DC motor or AC motor, and then from there you design the circuit and then you explain and come up with some calculation. Okay, so this is like an extended assignment, and also there may be a quiz as well. Okay, the quiz, that means it can be a simple quiz form like in the Google or in any other form as well. So this will be total added up to 40%, okay, of your final assessment. Okay, but yet to be confirmed, just to let you know that, okay, because the faculty has to standardize the format. Okay, so they will call for meeting by this week, or okay, until so that by next week I will know the final format. Then I will discuss with you. Then I will set the date for us to carry out the final assessment. And then the final assessment, right, this one will be conducted during the lecture time, so to avoid in clash with other topic. Okay, normally the final assessment, maybe the MCA, multiple choice, MCQ, okay, not MCA, multiple choice question, right? Okay, MCQ is a multiple choice question, will be conducted during the lecture. Okay, so maybe 40 minutes, something like that. You need to answer a certain amount of question, then submit the answer through the Google Sheet, yeah, or Google form. Okay, this is the assessment. It will be conducted during the lecture time. Okay, all right. So any question from the floor? So if no question, then I will continue with our this last chapter discussion. I will just go through it very quick, because this is normally the base drive circuit, right, is already done by those chip, the IC. Okay, this IC chip is already controlled by the IC chip, because IC chip can have a high precise and reliable drive signal, the PWM. So that's why now they have a lot of the base drive IC available in the market, okay, to generate the correct PWM with the proper setting or proper design of the component inside, so that your switch can work, okay, can turn on and turn off as quickly as possible. Okay, so In this chapter, we will cover about the drive circuit design consideration. So we will consider, okay, what is the component to be considered when we design the base drive circuit, such as the energy that's stored inside, okay, the capacitor, how to remove it, for example. Then the reverse recovery time, reverse recovery charge inside the PN junction, how to get rid of this disturbance inside the base drive. The second one is the DC couple drive circuit. That means how to do the coupling, how to couple the signal from the one side to another side. So it's coupling circuit. And then we have also the how to isolate, okay, between the primary side and the secondary side. So this one normally is done by the transformer or done by the optocoupler or opto isolator normally. So the objective is to identify the gate characteristic and requirement for BJT, MOSFET, or IGBT, for example. Okay, so in order for you to develop the base drive circuit, you need to first understand their switching behavior, whether it is driven by the voltage, or it is driven by the current, or it is driven by the pulse, okay, kind of thing. So you need to understand the behavior. So design the gate and base drive circuit for the converter. So basically in the converter, okay, you have the buck converter, you have the push converter kind of thing, right? So for example, we have the simple simple buck converter, for example. Okay, so this is the buck converter. So the key here is that how to design, okay, the base drive circuit. The base drive circuit actually is referred to here, okay, the base drive. They can generate the very nice PWM to drive the on-off of the BJT or MOSFET or IGBT. So this is the switch here lah. So this is the purpose of the base drive here. Okay, so base drive actually consider one of the very important, okay, important component in the converter design. Yeah, if you do not have the good PWM, then your accuracy, the efficiency, all will be affected a lot. So that's why the base drive is very important here. Okay, but however, most of this base drive signal, right, is now being controlled by IC, okay, IC chip. So that's why, because it's already like fully customized, okay, to their according to the different behavior. And then also to develop the isolation techniques interface in between the low power drive and the high power drive. For example, I have for example the BJT, right? Okay, the meaning of the low power and high power is like this. Let's say for example, here I have a 100 volt. So here I only have a 10 volt. So here is considered the low side. The low side is to control the high side. So this is actually the purpose of this. By the way, in the base drive circuit, I need to design so that the proper isolation, okay, can be implemented, so that to avoid the direct contact between the primary side and the secondary side. So that by using the optocoupler or use transformer to isolate. So there are many ways to do it. Okay. So in general, you see the base drive circuit is that, so you have a control circuit. So basically the control circuit is to trigger the drive circuit to generate the PWM. So this is the general idea, so that you can turn off and off, okay, according to the design specification. Okay, especially when you are driving at the high frequency. So the accuracy is very important. Okay, in certain circuit design, let's say for example, then they switch on and off the time, right? So practically they will have this kind of waveform, okay. But in some circuit design, if the if the base drive circuit is not so good, so they will contribute to a lot of losses, such as, for example, the loss at here, and also the loss at maybe here. Okay, they will have this kind of the losses. Okay, the losses here. Okay, so this is called a switching loss. Okay, this one is like I forgot the name. This is also another kind of losses. So you need to design. This is due to the storage charge inside that make it to become the switch to become saturated. Okay, all right. So the interface between the low and the high side, right, can be controlled by can be isolated using the optocoupler. You see, so basically, this optocoupler work exactly like a normal BJT. It's just that now it is wireless. Okay, they use the light as a medium to control the high power side. So basically, it works like a variable relay. Okay, variable or adjustable relay in general. So the function of the gate drive circuit is that to properly turn on and turn off. This is ideal. Okay, when I want to turn it on, it will be turned on as fast as possible. When I turn off, it should be turned off as fast as possible. So some of the idea behind this base drive circuit design is to what are the methods of or the circuit design I can use so that the process can be happen faster. Okay, such as, for example, to minimize the turn on time through a different method to how to release the charge or how to push in the current fast so that it can have a faster response, for example. Okay. So any question on the floor? You can talk also. You can talk or you can type. Okay, because I turn on my speaker as well. Okay. So when I want to turn off, also the same. So how to when I turn off, right? Because there are always the storage charge inside the PN junction. Yeah. So they need to design a circuit so that I can actually drain away the energy inside the gate, okay, of the semiconductor material to dissipate their energy inside, so that I can something like a reset, okay, to reset the switch. So there are circuit to do this kind of job, okay. Then to provide the bias to ensure the power off switch remain off. When I want to turn it off, so make sure that you can maintain it on at the off status. And then to control the power switch to protect it when over voltage or over current are sent. This is normal. So this is to ensure that your switch will not be overloaded under any condition. So they must have some degree of protection inside. Okay, so this is some of their justification. They said the signal processing circuit which generate the logic control. The logic control means the one that generate the high or low signal. Okay, this one, okay, is not considered as a part of the drive circuit, because the drive circuit actually is used to drive the MOSFET, but the digital circuit actually is for the processing only. So by the way, this is very hard to justify lah. You can say the logic control signal as a part of it also can. You say not a part of it also can, because it is very hard to justify this. So the drive circuit amplify control signal to level required to drive the power switch. Okay, PWM is a part of the drive circuit, PWM, but the process to generate the PWM, for example, in the chip itself, right, in the IC. So the output here, the switch output here may be a PWM, but inside the circuit, they may contain a lot of the flip-flop, okay, the drive circuit kind of things. So the logic gate inside that generate the digital signal is not considered as a part of the drive circuit. Okay, but that's why I say it's very hard to justify. Okay. The drive circuit has a significant power capabilities compared to logic level. Okay, logic level just is a very small power. Okay, very power. It's not capable to drive the logic signal is not capable to drive the switch because they may not be have a sufficient power to drive the MOSFET and also the BJT. And then to provide the electrical isolation when needed. So basically, there are different kind of the drive circuit to drive to turn on and off the switch. So this one actually is referred to the practical switch. Ideally, it should be like this. Ideally, it should be like this. So there will be have a instant transfer from low to the high. There'll be no delay. But in the practical, there'll be some losses. Okay. So this one is just like a unipolar signal. Unipolar means only got one side, like a switch, like on-off switch. Here's the off, here's the off, on. So on-off switch. Okay, unipolar signal. This is only the input signal to drive the circuit. And also it can be a bipolar. A bipolar means like a repetitive pulse signal like this. Okay, so I have a bipolar, high and low, okay, polarity. So that's why we call it a bipolar. So it depends. It depends on the drive circuit requirement. Okay, depends. Some of the base drive circuit require this kind of waveform. Some of the circuit required only the unipolar waveform. Okay. So this is to provide some protection over current. Blanking time. Blanking time is referred to the time between the, let's say for example, I want to have one switch, then there'll be another lower switch. Ideally, it should be continuous like this, right? But because there are some delay, okay, some delay between the transistor. So this one refer to the blanking time, okay, or buffer, okay, the blanking time. The time before, for example, one BJT turn off, another one haven't turned on yet, so there are some delay on it. So it's a delay time or blanking time. So besides this, they also need to take care of other circuit parameter as well to control their transient. Okay, the IDT is referred to transient, that is like a spark, okay, or the spike that control the BJT to turn off. Anti-saturation is actually a circuit to avoid the BJT become too saturated. That means too full, too saturated. If too saturated, then it is actually quite hard to remove the charge inside. Saturated means like this, okay? Like for example, this is IC, okay? IC, this is the IB, okay? So you know that, right? The IC equal to beta IB. So by following formula, this formula is only valid before BJT achieve saturation. Okay, that means before the BJT becomes saturated, this formula is valid to be used for calculation. But when it becomes saturated means that the channel here, the current is already full. Okay, saturated. Saturated means that you increase the IB, but then the IC saturated. It remains same value. It will not change. Once you achieve the saturation, that moment, the beta that we use at the moment we call as a beta force. Okay, it's the IC saturation over the IB. This is the beta force. Beta force is applied after your saturation. So normally it's like this. Okay, so here is beta, right? So above, so here is the saturation. So here we use the beta force, and then below that is a normal beta. Okay, beta equal to IC over the IB. So here is IC saturation over the IB. So this will give you some basic difference. Okay, this is after they achieve saturation. Okay, saturation means the channel is already full. You cannot increase the IC anymore. It is overload. So if I operate my circuit right in the full saturation mode, that means it is very hard for me to remove the charge inside. So this will affect your switching speed of the BJT. That's why the BJT having the lower speed compared to the MOSFET. Okay, so speed up capacitor. That means there are some capacitor inside to make it switch on and off faster. Then the front push and back push current. That means this is the delay current inside due to the minority current. So that one we can see later on. So we try to take a look on the base drive circuit for MOSFET. Yeah. So you know that line, the MOSFET, first you know, okay, MOSFET is the voltage control. Okay, it's the voltage control device. So let's say I have a piece of the MOSFET. Yeah, N-channel MOSFET, right? Okay, this is the MOSFET. The drain, the source, they'll be cut off, there'll be no continuity. Okay, like this. So here the idea is the gate here. Okay, how to give the proper pulse, the proper voltage, so that it can turn on, okay, and turn off accordingly. So when the gate is on, is high, then it will trigger it to turn on. Of course, you need to have a sufficient VGS here to make it on. Normally the value is about 4 watt, for example, 5 watt, for example. It's quite high sometimes. Okay, the pulse required. So you need to make sure that you need to have a proper drive to make it on and off as fast as possible. Okay, MOSFET is a voltage driven, not current, because for the MOSFET, the input resistor is very high, so there's no input current. So basically, ideally, IG equal to 0. Okay, remember this. So the MOSFET on time depend on the time constant. Time constant means actually there are some capacitor in the front here, the control circuit, to control their on off. Okay, we take a look at the next one, and also the external capacitance value. Yeah, for example, this one is the base drive circuit for the MOSFET, right? This one is the whole of this actually called their base drive circuit, this portion. So we need to see from the capacitor behavior. Okay, so when you first turn on the time, right? First turn on the timer, the voltage will slowly build out at the capacitor. And in other words, the capacitor start with short circuit first. Okay, because before I turn on the power, right? So capacitor basically is no voltage, so it's short. But when I switch on the switch, so the voltage will slowly charge up to the capacitor. So that means it will charge up in this way. Okay, the VC, so it will charge up slowly like this until they achieve saturation. So that's why they always start with the short circuit here. So when you short circuit, so basically your IG, the gate current, is only controlled by the gate voltage and also the source resistance. So that's why you have the gate voltage like the gate current like this at the beginning, But at the steady stage, when this one is been charged up to maximum, so here will follow the simple voltage across here is what? So never mind, it's just following the voltage divider rule, so that the gate voltage, VGS is voltage across here, is depend on this gate resistor. Normally this gate resistor is very high, it's very high value. Up to the mega ohms one, actually is up to mega ohm. It's very normal because they want to block the current flow in. So by this, according to the voltage divider rule, right? So your VG, okay, VGS, so its VGS is here. Gate to the source, VGS is equal to, just like a voltage divider rule, RG, so RG plus RS plus R. Then you multiply with the VG. So this will give you the VGS at the steady stage, at the steady stage. And then this one is so-called the Totem pole gate drive circuit. So the purpose of this circuit, right, is to actually to make sure that it can turn on and off at the accurate design. So actually very simple. Okay, you see, here we got the one comparator. Comparator means we compare whether is V in is high or the feedback is high. So this capacitor will charge up based on this VG here. So here is VG. So they will charge up here up to the VG. So this VG will compare with the V in. Okay. So the idea is like this. If VG is higher than the V in, that means your output is high. Okay, output here is high. That means here will be a high. Like this, the high. So in this case, your NPN BJT on. That means this one will be on. Okay, this one on. When it's on, it will like a short circuit. So the current, the main current will flow this way. Flow this way. Okay, that means there will be a voltage built out here. So it's a VCC. Okay, get that? Because here is a short, right? It's a short. So the main voltage will fall at the open circuit here, VGS here. So the VGS here will be like a VCC. So it will turn on the MOSFET. Okay, it will turn on the MOSFET. But then, if in the case number 2, this is case 1, the case number 2. So if the V in now is higher than the VG, the other way around, so it will generate the negative pulse like this. Its comparator means it's either high or low only. So in this case, for the case the bottom side, it will be a negative pulse. For negative pulse, it will on this one. It will on this one. Okay, I used a different. Sorry, I used a different color. Okay, I repeat. I repeat this portion because I want to explain with the different color. Okay, right. So case number 2 is that if the V in now is higher than the VG, the gate voltage here, so that means your signal will be at the bottom side. It will produce a negative pulse because it's negative higher than the positive. Your output will become negative. It's a comparator. So here will be a VCC. Then here will be a negative VDD like this, okay, positive, negative. So it will swing to the negative VDD here, okay. So when it goes like this, so that means there will be a one negative pulse here. So this negative pulse will trigger this one on. So here will be on, okay, here on, here will be off. So when it is on, what happened? If this one is on, right? So that means let's see. If they're on, right? Okay, so basically here will be short. Here will be short. On means it's short, right? When it's short, the VGS now becomes 0. So that means eventually you will off the MOSFET. Can you see the behavior? Okay, when the V in is higher than your feedback VG, this is VG, right? So it will generate one negative pulse. So this negative pulse will turn on the PNP transistor because it's a PNP type. So when the PNP is turned on, that means here will be short. Short. Here is open. Upper side is the open circuit. So here will be short. When it's short, that means it will short the VGS. So VGS becomes 0 voltage. When it's 0 voltage, that means it will turn off the MOSFET. Okay. So it will, all the voltage here will drop to 0. So it will turn off. So this is basically the so-called the Totem pole gate drive circuit. Actually is all of this is in charge by the IC inside. Okay. So this is also same as the explanation I explained just now. So okay, the second one is about the BJT. BJT is slightly different because BJT contains the minority carrier. Okay, so what I do is that you see, the switching time can be improved by reducing the on time and the off time. That means it can turn on and off very fast. By the way, to turn it on, it can be realized by pushing the IB to a maximum with a low force beta. That means, see, because force beta is a condition where the IC is already saturated, okay? It's already maximum current flow. So what I do is that I push it, I increase IB. This is normally referred to what? Overdrive lah. Remember what we did before? Overdrive factor. By 5 times, by 10 times, for example, you increase the IB value. Actually, the IB can be controlled by controlling the resistor here. Actually, it's very simple. Like this, for example. You control the R. This is a VB, for example. Okay. So here is a VBE. So because I know the VB equal to IBRB plus a VBE. So I need to control the RB value. So the IB equal to VB minus VBE divided by RB. See, if I reduce the RB value, I'll be able to increase the IB. So by this, I'll be able to control the overdrive factor. Okay, remember that if I increase the IB value, the IC will not change because it's already fully saturated. Okay, so that means I give the too much of pressure, the push, okay, the push very hard for the BJT to work as a switch, so it can turn on very fast. But if it turn on very fast, after turn on, the beta can be increased. Beta can be increased means I slowly reduce the IB value. That's why they need some programming inside lah. Yeah, normally it's controlled by the IC chip inside. Okay. After on, okay, then I will slowly reduce IB. This one is important. I need to slowly reduce the IB, but they still work as a switch. I cannot push this to the hard saturation all the time, because if I push very hard, it is very hard for me to turn off later on because it is too much pressure inside the BJT. Okay, that's why after I turn on, I need to slowly reduce the beta. This is some of their design consideration. And then the switch off time can be reduced by reversing the bias current. That means you suddenly reverse the current so that it can help to drain out the current very fast. So the purpose is to discharge it, to reset the BJT. Okay, this portion, the reverse current, because the BJT is formed by the PN junction, right? So it's a reverse saturation current, or pit inverse current is the same. Okay, so we need to control BJT, switch on and switch off, proportional base control, anti-saturation control. Okay, so this is the behavior that you need to take into consideration. So this one is the on circuit, yeah, the on circuit. Make it case simple. For the on circuit, because they work at the very fast speed. So assume that, just always remember that, okay, when the V, it's not VP, like V1, okay, V1 just turn on the time, right? The C1 is short. Just remember this behavior because they work at a very fast speed. When you switch on the time, or the voltage just started to build out, so it start with the short circuit. Okay, the voltage here. So it's like this, slowly increase until they achieve saturation. So here is a VC1 like this. They increase to up to the V1. Okay, so that's why when the circuit is just turned on, C1 is short, so they will give you the IB1. So it means the initial current, IB1. Okay, it's the initial current. So this current, it work like a pulse. Okay, no, work like a spike. So like an initial spike that can trigger the BJT turn on. Okay, like a spike, because it will when it's first turn on, it will very fast. Then it will slowly reduce because of the capacitor. Okay, when the capacitor increase, then it will slowly reduce until they achieve the stable IB. Okay, so after capacitor they charge up, so it will charge up to, I don't know what's the value, so maybe a higher value. Then in this case, R2 will take the function, so that your IBS is saturation current, means they achieve stable. So here is IBS. Sorry, it should be, yeah, correct, is IBS. Here is IB behavior. So here is IBS. They achieve saturation. So that means the IBS is V in minus the VBE divided by the resistor in the middle, R1, R2. So it's very simple circuit analysis. So if you ignore the VBE, the capacitor will charge up to maximum. So they will charge, because the capacitor, right, this C1 will charge according to like a voltage divider. If you ignore the VBE here, so basically they will charge up according to the voltage divider rule. So they will charge up to this one, the VC. VC is R2 over R1. Okay, if you assume that the VBE is very small. And finally, the charging time is approximate to this value. Okay, R1, R2. And then the reason is that because is that this R1 parallel with R2 times C. Like this is actually the formula. The T equal to CR, but R is a parallel of these two together. Actually, if you ground the base terminal, actually these two work like a parallel one. Actually, there are certain method to analyze it actually. Okay, so that's why R2 in parallel, you get this formula. Okay, formula is still the same. The T equal to CR in general. So someone stop the recording. Okay, it's okay. So make sure that you keep track of your recording if you want to keep the record. Okay, let me continue. It could be quite fast now. Okay, so this is the turn on behavior. Okay, the BJT turn on control. So it's the T2 is C1 R2, but this is happen when the switch is off. When the switch is off, so the capacitor will discharge. So they will discharge through this loop. So the discharging time is equal to C1 R2 because they discharge through the loop here, internal loop. Okay. So and also this one is the formula to determine their switching frequency. Okay. So in order to allow the sufficient charging and the discharging time, the T1 is set to be at least 5 T1 and T2 is at least to 5 T2. This is because when I switch on, the capacitor requires some time to charge up and also to discharge. So in this case, I need to set my frequency, the on time and off time frequency, that 5 times, okay, 5 times the T1 and then the 5 times the T2. So they have a sufficient time to charge and sufficient time to discharge. So this is actually the design consideration. If I turn on and off too fast, for example, I set my frequency to be too high, so the capacitor may not have sufficient time to remove the charge inside. So after the few cycle, then the capacitor will become saturated. Okay, when it's saturated, then you will not be able to control the switch effectively. So for the BJT off is also the same. So when the off at time, right, they try to avoid, okay, the the energy that's stored inside the capacitor to hit on the BJT. So this can be done by using this another network here, so that the charge inside will be dissipated inside the loop itself lah. Okay, so that there will be no spike that strike the feedback that strike on the BJT. So this is something the idea. Okay, so for the rest of the reading you can read by yourself. And then this one is called a proportional base drive circuit. Is something like this. Proportional base drive actually is referred to the so-called regenerative behavior, because it will be able to self-sustain. Okay, self-sustain. How it works actually is very simple. Okay, first, right, you see this one actually is to provide when the switch is on. Okay, it on, so it will turn on. This is when it on, right? Here on, then it will turn on the BJT. Then IC it turn on, then the current will flow down. When it flow down, because here is controlled by the transformer turn ratio, right? They control the ratio between the N2 to the N1. They control the turns ratio. Okay, so what happens is that when the current IC pass through here, so it will induce into the N1. Okay, the N1 will generate the IB. So that means the IB here will control the N1, N2, and then it's IC like this. So if the IC is increased, then they will induce the certain amount of the current into the N1, then it will produce the self-sustained behavior, so that the BJT, right, can self-regulate by itself. That's why you call a self-sustained behavior. This is a formula, right? N2, N1. So IC, IP is N1, N2. So it's the same formula. Okay, this is some of the design. So anti-saturation. Okay, just remember one thing. The purpose of the anti-saturation is that to avoid the IC here to have too much of the current inside. Okay, so that I can switch off faster. So this is the general idea about the anti-saturation method. If I remove, actually this portion, this circuit actually is used to control the anti-saturation behavior, so that when this feedback, right, through the base to the collector, they will feedback with 1 VCM. So they design such a way that the VCM is higher than the VCE, so that the IC can be controlled by this formula. Okay, by increasing the VCM, I will be able to reduce the IC, so that I can actually like clamp circuit, clamp, you know, right? CM actually is referred to clamp. What's the CM again? It's a clamping voltage. Okay, I can limit the voltage to certain level, so that it won't go to too deep of saturation. Okay, I can clamp the voltage like a clamping circuit inside. It's an explanation. So I no need to explain in too detail. Just remember that the purpose of anti-saturation is to avoid, okay, the connector current being saturated too much by controlling using the clamping mechanism, okay, or clamping voltage, VCM. And then isolation is another one. Isolation is basically it work like a separator. Okay, isolation is a separator. Okay, separator to separate between the primary and the secondary side. So this is purpose of the isolator. Okay, so normally look at the HPH, right? You have 4 pieces of the switch. Normally for the low power device, you can use the circuit drive here immediately. For example, this is the N-type, right? This is N-type. N-type, I need to give the positive pulse to turn on. So here's a positive pulse. Here's the N-type also. Here's a positive pulse. Okay, to turn on. So when I have a positive pulse, so it turn on, so it can run like this direction. Okay. Later on, if I control the second part. So this also all is N-type now. Sometimes it can be the one pair of N-type, one pair of P-type. Sometimes it depends. So here also the same. If this one is high, here is a high. Sorry, here is a high, and then here will be turned on, so it will flow this way. So you can see this is actually how you can control the direction of the polarity of your device, the motor device or other device. So normally in the low power device, no isolation is required. It's okay because normally the power MOSFET or power BJT have a high power handling capability. This 4 pieces. But in the high power motor, right? Because the high power motor, the feedback, okay, the transient or the harmonics from the switching on off of the motor is very, very high. So they need to have some sort of isolation. So this is isolation required. Okay. They avoid the direct contact between the drive circuit over to your high side. Okay, so this also can be done. This is also another method. You see, this is they use the optocoupler. So optocoupler is one of the very popular option in the base drive circuit design. But all of this, right, is already available in the IC form. That's why normally in the nowadays, all the manufacturer will just simply buy the IC, then you will just directly configure the IC to drive to the MOSFET. So the thing become very, very compact and neat nowadays. Okay, become very, very precise in the design because this circuit already like fully customized. So you don't need to design from the beginning nowadays. Okay, so this is the Thyristor. The one you know, right? Thyristor. Thyristor required the gate circuit to turn on, but this one is also use the optocoupler concept. So something like this. So here there is a sensor here also, sensor. So when the light is emitted from the LED, so it will be a receiver. When they receive, so they will trigger the Thyristor to turn on. When it on, then it will trigger the output component to turn on as well, SCR. So this is the this is also the same thing. Okay, this is the optocoupler or opto Thyristor. So UJT, I think you know already, right? UJT, or you already did this for your lab session. Okay, so UJT basically is a kind of like a PN junction only. So it's not it's different to the BJT, different to the BJT and different to the MOSFET because it only contain one P and N junction only. So it can be equivalent to this circuit. This value is a fixed one. Okay, the top one is a fixed one. This is adjustable. This is the equivalent circuit. So this is the IE, the emitter current. So what happens is that they will be able to generate this kind of pulse. So this one can you see from your lab, right? Okay. Normally the UJT is used to generate the pulse to drive other circuit, such as for example the pulse to drive the SCR. Because for example, right, the time I turn on, so they will charge up T equal to CR1. So it's a charging. So they discard the waveform. See the charging, charge. When they charge up to maximum, when they reach the certain threshold, because it's a PN junction, right? So normally it's a 0.7 volt lah. Here's a PN junction. So they will discharge. So this is so here is a charge. So here is a discharge. Discharge very fast one lah. So they will be able to generate the one pulse here. See the discharge part. So here is a discharge. At the output side, this is a discharge. So here is a charge. So when they discharge, they will be able to generate the pulse. This pulse will be able to drive the gate of the SCR to turn on. Because you know, right, the SCR is a kind of the control turn on, but uncontrol turn off. For example, you put the buzzer here, very big buzzer. So one, you get a signal from here, it will trigger it, it's short. When it's short, so it will make current, maximum current will flow. So the buzzer will sound. It will sound until no end, until you cut off the main supply. Okay, so this is the UJT. Okay, so this is what we have for the UJT. Any question from your side? So in general, this is the end of our lecture. Finished already. So in order to I just want to repeat my planning just now. So this is the end of our lecture. So there'll be no class on this Thursday, no class on this next week as well. By the way, please follow this planning. Okay, this planning. To those who joined our class late just now, okay. So this is for today. So we finish all the lectures, done. So Thursday no class because there are certain issue that we haven't cleared out yet, so I cannot confirm their format, for example, the final assessment. So no point for you to tell you the detail here. So there'll be no class. Here will be no class as well the next Tuesday until the next Thursday. There'll be a final revision. Okay, in this revision, it's very important. In this revision, I will tell you the detail of our final assessment. Okay, so what is the date, the time for the assessment, and also what is the format available, maybe the multiple choice question, the extended assignment or quiz format. So by the way, at the moment, I'm still not sure yet the actual format to be used, but 40% is for sure. Okay, 40% for your final assessment. Okay, so I will see you again on next week Thursday for the final revision and also the final format, the assessment format. Then later on we will stick on this on the planning. Okay, any question from the class? Okay, so if no question, okay, and good luck, and then you please study and then complete. Try to complete